Okay, good morning, ladies and gentlemen. Well, it's my greatest honor to be the one to introduce our first keynote speaker, Academician Wang. Professor Wang's brief profile is on our program books, page 19. He got his PhD in atmosphere science from University of California, Los Angeles. And he joined the faculty of University of Wisconsin-Madison since 1980. And he served as the chair of Department of Atmospheric and Oceanic Sciences in 1994 to 97, and the first chair of Air Resources Management Program in 1998 to 2002, both in your Wisconsin-Madison. Professor Wang's research field is in atmospheric science. Aside from his specialties such as cloud microphysics and cloud dynamics, I just learned from our brief conversation that he also paid attention to the historical climate change. So he has constructed a digital historical climate database derived from climate records found in Chinese official chronicle, local gazetteer, and various kind of related documents. So this database is for the benefit of the international climate researchers. And today he's going to share with us why clouds are not innocent at all. So without further ado, let's welcome Professor Wang to the podium with a big round of applause. Please.
Good morning, everybody. Thank you for your introduction, Professor Chen. It is my honor to be invited by PNC to give this talk, and also it's a great pleasure to give this talk here this morning. Okay, like Professor Chen said that my real expertise is really in clouds, and that is the reason why I choose to talk about clouds today. But it is also related to the topic that of the PNC talking about the uncertainty, as cloud is related to climate, and climate is at least one of the biggest uncertainty facing our society these days. Okay. Everybody should have seen clouds before, even people here in Tucson. Sorry to say that, but all I want to say is that Tucson is a relatively dry place compared to places like Taiwan. So this picture was what I taking in Academia Sinica, just out of our building's window, and I can watch that clouds formation every day. And I always joke that one of the benefit of studying cloud is that you can always look outside the window. If you are university or academia bureaucracy come to say, how come you're not working? You are looking outside. And I say, I'm working because cloud is my topic. So. Indeed, it's very interesting. You can see that the cloud changes all the time, and as one of the old Chinese proverbs says, the famous character of cloud is that it changes all the time. So in Chinese it's called 世事云千变. The cloud changes all the time, and they are all over. This is over the sea surface in the northern Taiwan, and you can see these very convective clouds, which we call cumulus. Okay, so this is cumulus, and you ride a high-speed train across in Taiwan, you can you see this type of cloud all the time. Like I said, you probably don't see this much cloud in Tucson as much as you can see in Taiwan, because Taiwan is a very humid place, and clouds needs water. Various kinds of clouds, you wonder if you ever wonder what happens. I was very interested in cloud ever since I was a child. And of course, my father was backed by me. Also, all the questions about why this about cloud, why that about clouds. Of course, he couldn't answer, because back then nobody really knows too much about clouds all about. And eventually I went to university and I studied, my field was in meteorology. Surprisingly, people did do some observation about clouds, and they talk about the cloud classification. But relatively few people know anything about the physics inside cloud. So I finally decided to make my special field in studying the physics of cloud. And that's why I ended up in this cloud physics and study clouds. So, at least for more than 40 years now, I've been putting a lot of attention on the cloud science. Okay, so cloud like this is a thundercloud. This is the cloud that produces thunderstorms. And if you ask me, how do you know that? Well, I knew that because I studied this for more than 40 years, and there are various signs that what you can produce. Somebody will say, well, every time you see this type of cloud, this is called autocumulus, and every time you see this autocumulus, it's good weather, and of course everyone knows that. You don't need to watch the sky, just walk out and reach out the window. Your hand is not wet, then it's good weather. That's the way it should be. But this is indeed a sign of good weather. So let's look at this some more. This is a so-called cumulus, cirrus cloud. So it's a high clouds, and you can see it looks very different. And why it is different? Well, first of all, these are ice. So clouds are not just water, just liquid water like most people think, but they can be ice, like this. If you're in trend, you know that this is called cirrus, and they're ice crystals. And why they're ice crystals? It means that the environment where these clouds form is very cold, and so these liquid water cannot exist, but it has to be ice. So these are the various facts about clouds. However, let me talk about our main topic here. So I don't want to discuss the various kind of clouds, but just want to say what are the impression of cloud of most people. And sorry, I have some Chinese character here, and I believe some of you know very much about it. If you don't, you can ask your colleagues here. They can tell you. But at least in Eastern culture, and in Chinese culture, cloud has this character of very freely floating. It appears to be a leisurely object, and it seems to move from here to there effortless. And so I listed a few ancient poems or verses, and people describe somebody's writing style is very flows very smoothly. They describe it as like a moving cloud or flowing water. So this is 行云流水. This is one of the old saying. Or somebody has this very chaotic, well, not chaotic, but very leisurely life, and without too much bounds in life, we call them 闲云野鹤, right? Like a leisure cloud, or like a wild crane, which is fly freely, or some Buddhist monks who wander from one place to the other, and we call them cloud and water monks, 云水生. So I look up the definitions, and I think it's somewhat different from what in Western society what you call the wandering priests. I think the style very different. However, I have to say that I'm quite a layman in Buddhism, so if I say something wrong, please correct me. Okay, so that is our common impression on cloud. And I feel that cloud is something very leisure, not very working very hard, and have a good life. And, so that you will think that this cloud just there, like an innocent bystander and doing nothing. And I want to tell you today that no, it's not so. A cloud actually busy doing work and doing their share of the work in our atmosphere, and I will tell you why. So these are just the general impression of people's cloud. And so first of all, why are there some characteristics of a cloud? One is that the clouds seem to have much to do with mountains. So one of the questions I always asked my father when I was a kid is, where do clouds come from? His answer always is that clouds come from mountains. And I always say, how do you know that? He said, well, because the book says so. So there was a Chinese phrase called "yun cong shan chu," the mountain, the clouds comes from the mountain, And so there are a couple of these verses or poems in the Jin Dynasty, Tao Yuanming, talking about these clouds being out of the mountain, and these famous scholar during the North and South Dynasty also mentioned about there's nothing in the mountain except there are a lot of clouds. But I can only enjoy it myself, and I cannot give it to you as a gift. And of course, you cannot really grab a piece of cloud and give it to somebody else. The cloud is really not a very reality entity, Somebody say a cloud looks like a cotton ball, but a cotton ball is a really coherent. Cloud is not. You try to grab a piece of cloud, it disappears in your hand. One of the artists in Taiwan that I admire most, and is the late Professor Huang Junbi, who is very famous in painting these traditional Chinese landscape and with a lot of clouds. He even called himself the master of the white clouds whole, Baiyun Tan Zhuren. So that's very interesting. It's very nice. But you just take a high-speed train across Taiwan, and you can see that it always almost have these clouds around mountain. But why does that? Every time when I was young, I went to a mountain. I want to see is there really a hole of clouds where all the clouds are really coming out? And of course, I was always disappointed. There wasn't any particular place where you have a lot of baby clouds there and then suddenly pop up. None of that. And they are everywhere. They are over mountains. Small mountains like this one to the left. This is in northern Taiwan. Just by the small mountain, you can see these very tall clouds. Or you can have these very high mountains. This is one of the pictures I have taken. One time I flew through western China, and you can see that those mountain peaks all have snow covered. So it must be very, very high peak. But yet you still have these clouds flying above it, And so how does cloud come about? Over the vast ocean surface, you also have a lot of clouds, and a lot of mystery what can happen. So in meteorology, you do have a cloud classifications, and let me just mention it very, very briefly. In meteorology, the clouds are classified into 4 types based on the cloud height. One is called high clouds, with cloud base higher than 6,000 meters. And the middle clouds is based between 2,000 and 6,000 meters. Low clouds with cloud base less than 2,000 meters. And then there is clouds called cloud with vertical development. These are the clouds with the base very low, but the top very high, almost like 10 kilometers or higher. Okay, and again, this is not the purpose of our talk here. So let's look at how do cloud form. Here, the air has to go up. That is how the cloud should form. And why? Well, our atmosphere is a very special entity. And it's very special, especially in the vertical direction. In the horizontal direction, it's just like any other gas. But if you go up, one thing will change very quick is the pressure. And along with the pressure, the density. So both density and pressure of the air decreases very quickly if you go up. So if you travel up to the mountains, somebody will start to get problems of breathing because the air becomes thinner. And as the air becomes thinner, you don't get enough oxygen, and your body starts to feel it. And so that is one of the signs saying that the pressure has become less. But what's the importance of this less pressure? Well, the fact is that suppose you have a parcel of air, which we call an air parcel. When the air parcel, the size is arbitrary. Let's say there's an air parcel about the size of this room. Suppose there's some force that make this air parcel to go up a little bit. What will happen to this air parcel? Well, one thing we do know that because when you move up, this air parcel immediately experience the fact that the pressure around this air parcel decreases, so it becomes smaller. And once the pressure becomes smaller, there is not much pressure outside, so the air parcel has to expand. So what will happen is that the air parcel will expand. This is quite similar to a balloon, If you ever wonder what's the fate of a balloon going up. When a balloon goes up, the air above becomes less pressure, and the balloon will expand. It keeps expanding, and the balloon is not built very strongly, it will pop very quickly. So some of the not so high quality balloons will pop very quickly. It's a sign saying that the balloon will expand. The same thing for air that is starting out from the ground. When it goes up, it will expand. That is the fate. You have to expand because pressure decreases. But when the pressure decreases, what will happen to this air parcel? Aside from being become bigger, the air becomes colder. This is called adiabatic expansion cooling. It's a bunch of technical words. But what essentially is saying is that if the initial energy of this air parcel is very constant, when it goes up, it expands. When it expands, theoretically, it is doing work on the outside. So it spends energy to expand. And when you do the energy to expand, you are something in you, the energy should decrease. So that part of the work that you have done, the energy should decrease. And that is taken out from the heat of this air parcel. So the temperature becomes colder. So every time when an air parcel goes up, it will expand. And that expansion results in cooling. Okay, so we can even calculate how much cooling it is. And it's about 10 degrees Celsius per kilometer. If the air goes up 1 kilometer, it will cool down by 10 degrees C. If it goes up 2 kilometers, it will cool down by 20 degrees C. That's a lot. If the air parcel start out here, it's pretty much like early this morning, temperatures about 20 degrees C, and somehow we make it ascend 2 kilometers. that air parcel becomes 0 degrees C, very cold. It expands quite a bit, but it becomes very cold. All right? So what will happen? Suppose this air parcel contains some water vapor in it initially. Now at the 20 degrees C, the water vapor is not going to condense because it's far from saturation. And we know that, because at 20 degrees C, you don't see much happening. But when it goes up and becomes colder and colder, eventually there is a certain point. That depends on how much water you originally have in this air parcel. It will become colder enough to reach a point we call saturation. That's the maximum amount of water vapor you can hold in a pack of air. Beyond that point, that water vapor will start to condense. And they will take out those extra water vapor that's beyond saturation. And so what's happening? Okay, so imagine this. You have a pack of air, which originally looked transparent. When it goes up, it becomes colder. It goes up more, it becomes colder enough, suddenly you have condensation because it's saturated. Saturation means that suddenly you see cloud appears. Okay? That cloud up here is meteorologically called the lifting condensation level with an abbreviation LCL. Okay? So the net result is suddenly you see cloud appears. Okay? So if you see that there is a small piece of cloud floating in the sky nicely, leisurely, freely floating, actually it had been working very hard from the beginning with a lot of water vapor and gaining energy and going up until it reaches saturation, and bingo, you see clouds there. If the clouds has more water, or the air parcel has more water, or there are other air parcels floating, continuing, following that original air parcel, you see the cloud keep growing and growing and bigger and bigger. So that's how cloud actually forms. Okay, so that is the point. You see that this figure to the left is how this convection, this is basically not just convective clouds, but almost all the clouds form this way. It has to go up, expand, cool, reaches this so-called LCL, and condenses. That's where the cloud base is. So this video to the left, to the right, will show you that. So you see that under the cloud base, it appears to be transparent. But you know that cloud is growing, is going up. Why? Well, it's not that because down there, below the cloud base, there's nothing. There are something. If you have these infrared eyes, then you can actually see a lot of these water vapor working, very busily and try to go up. You can even say struggling, going up, and finally at this LCL of bingo, you see cloud forms. And if the water vapor supply continues, then you see the cloud grows continually and eventually becomes a very large cloud. Okay, so that's the cloud movie. So if you watch carefully, and especially if you take long distance flight, which like this one, I did take this flight from Taiwan. You flew over a vast either land surface or water surface, and you can see a lot of these things. These are called cumulus. And the cumulus cloud in the morning, they are small. You stand on the ground, you don't see too many, and you probably don't see the structure. But if you are flying from above, you can see the structure very well. And you can see there are actually some structures. They are not completely random. And by careful study, you will find out this is more or less look like when you heat water in a pot. You try to boil water in the pot, and you see these convection cells. And eventually it's boiling. But these cumulus clouds indeed are convection cells over the surface, which means that you have heat below. The surface is hot. And why it's hot? Well, because in the morning the sun is shining on the surface, and the surface has become hot, and now you start to have just like you are boiling hot water in in your pot, and so you see these convection cells. So this is the beginning of clouds, and in the middle range, it will be similar to the movie we just seen before. But if there are not all this water vapor available, and the wind or the updraft is continuously strong, then you will produce a thunderstorm. So here is an example of thunderstorm. And you can see cloud indeed grow vigorously, eventually hitting a certain height, and it start to expand out. And once we see this expansion part, that is called anvil, because it does look like a anvil in a blacksmith shop, where you hammer various kind of steels. And in this process, a lot of these cloud particles and heavy rain, hailstones will form, hit the ground, and so on. So that is thunderstorm, okay? And lightning, thunder occurs in it. Okay, so you see, it's really not that complicated. All it takes is the cloud, a pack of air rising from below, start to go up, condenses, and give a lot of particles, eventually like this. Now, during the process of condensation, there's one thing that we have to remember is something called the latent heat, and I'm not sure you're very familiar with that, but it means that during the condensation, heat will be released from these clouds. So inside the cloud, it's actually relatively warm compared to the air outside, because these latent heat get released. And these released latent heat will promote more further growth of the clouds. And that is a very important part, because latent heat is a big amount of energy. So let's look at a summary. What happened really in terms of cloud formation? Well, you have this air parcel rising from the ground, hitting the so-called lifting condensation level, the LCL, where condensation starts to occur. Whenever condensation starts to occur, it means that energy will be released of the so-called latent energy or latent heat. It continues until the cloud finally ends. And there's no more water available once you go up, and all the energy, all the latent heat has been given away during the process. So overall, what does this mean? Well, it means that the ground was originally hot. This heat was carried by those air with the little water vapor, and they carry a lot of this energy up. And finally, they start to condense, they give the energy away, and then when they get up to the top, during the process, a lot of this rain, hail, or other kind of precipitation, maybe snow, can occur. And finally, that's where the remain of the cloud is above in a high place. So what is cloud doing? Well, formation of cloud actually carries energy from the surface of the earth to the upper level of the air. So that's the first function of the cloud as far as the energy is concerned. And so what does that mean? That means that the energy on the surface actually is taken away. So this figure shows you that if there is 100% of where is the light? If you see that number 100 there means that there's 100 units of the energy coming down from the sun. To go through the atmosphere, pretty much transparent. About 30% of the energy is reflected directly. Okay? So that 8 plus 17 plus 6 is 30%. That's called the albedo of the Earth. Another 19 plus 4, so it's formed by cloud and air and a lot of vapor in between. The remaining 46 go down to the surface directly, and that's the part that heats the surface. In the morning, when the sun hits the surface, it's going hot. Where does that energy come from? From the air. So 30% get away, the other some of them get absorbed in the middle, and heat the surface. Now, if that part of the energy is not taken away in a daily basis, what will happen is the surface will become hotter and hotter. It will become a surface warming. Now, in the long term, we call it global warming, but in the short term, even in day, it becomes a very hot day. So you need somebody to take that heat away. How? Well, there are various ways. So these red letters represents the way the energy being taken away from the surface. You can see that out of these 46, 15 was directly radiated by the surface. Well, because the surface gets heated and then radiate these heat away very directly. That's mainly the way how Tuson gets cooled is by this radiation directly spinning away. But in other places, like in Taiwan, where you have a lot of water vapor and a lot of possibilities for clouds, there's a lot of majority actually taken away. So you can see that the 7, 6 this is by this convection of the hot air. But 2D4 is by latent heat, which means that more than half of the energy originating on the surface in global sense was taken away by the cloud formation. So you can see that the first function that we know now that the cloud surface is to take energy away so that your surface is not terribly heated, otherwise it will be trouble. The surface will become hotter and hotter and nobody can move it. So cloud first played this very important function. And I just show you that this 46 and 46 on the right hand side add up. Right? So this happens, little story I learned. In the Tang Dynasty, this famous master, Zen master Yao San, Da Shi, who once upon a time my governor Li Ao, who visited him and asked him, what is Tao? I think that's the way that people in that time do a lot. Don't know if people do that in this center here, but and these stars didn't give him a damn. Let's put it in a vague way. But one asked, he just say, well, show him that there's a base of water on his table, I think. But then he pointed out on the sky there are clouds, and asked this governor, do you know what it means? And of course, this governor doesn't know anything, and so I'm just for fun. I'm just thinking that if I were this governor, I would answer what I just told you. Well, the water on the ground is somebody that haven't done his work yet, but those clouds, they have done a lot of work, carry a lot of energy, give out their energy, give out whatever they have, they ascended to high place as in clouds. So there's a difference. Both are water, but in a different stage. Well, I don't know, different stage of what, maybe different stage of enlightenment. Okay. However, that is just talking about the cloud carrying the energy outwards. So cloud also carry energy to the poles. So poleward. How does that happen? We have to know how climate of the Earth actually formed. The climate of the Earth, taking all the energy first from sun. So solar radiation hits the surface, and actually it's more like the sun radiates the energy in all directions. And the Earth in here intercept a little part of the energy. That little part, small part of energy decides what the climate of the Earth should be. And it's a complicated process, but that's the main process. What happens is that when you receive this amount of energy, you have to give away the same amount of energy. Otherwise, the Earth will be hotter and hotter. If it radiates back to the space, less energy than it receives, then what happens is that Earth will have more and more heat energy and become hot and hotter. And that's essentially what we are in these days. We are in because we have more carbon dioxide and we keep more heat. And therefore there's a somewhat imbalance. And that's why we have to watch out. So the balance is important. We have to give out this amount of energy. But this is talking about the global sense. Yeah, global sense, it has to be so. But locally, there isn't really a balance. Okay? So the chart to the right, the red curve represents the energy received from the sun. So that's called incoming radiation. And you can see that the curve is highest in the middle, where that is where the equator or the low latitude is, but it's much less in the polar regions, and that we all know, because in the low latitudes over the equator, you receive a lot of sunlight, solar energy, it heats up a lot. In the polar region, in the high place, not so much. Now, like I said, once the Earth receives those energy, it has to give back this amount of energy. But the ability of giving back the energy are not the same everywhere. You can see that the blue curve is the so-called outgoing radiation. Sometimes it's called outgoing long-wave radiation. It's in form of heat. So again, it is also highest in the middle and lower in the polar region, in the high latitudes. However, you can see that in the low latitudes, that red curve is higher than the blue curve. It means that in the low latitudes, it receives more energy than it gives away. So there's an energy surplus in the low latitudes. In the high latitudes, on the other hand, you can see that the blue curve is higher than the red curve. It means that the high latitudes actually give out more energy than it receives from the sun. Okay, so there is an energy imbalance from low latitudes to high latitudes. So there is a deficit in the high latitudes, and there's a surplus, energy surplus in low latitudes. Somehow this imbalance energy should be balanced by some way. Otherwise, the low latitude will become hotter and hotter, and the high latitude becomes colder and colder. So how do these energy balance achieved? Weather. So what's the weather for? Well, it looks like weather should have a purpose, but yeah, yes, indeed. It is the weather process that carries this energy surplus from the low latitude towards the high latitude. So every day we see this cloud formation. What does cloud do? It takes the energy from the surface, overheat it in the low latitudes, transport it towards the poles. All those processes, all those thunderstorms, they do exactly those functions in the atmosphere. Okay, so if I may quote another famous proverb in old days, just 天之道义，有余不不足. The nature's way is to use the surplus to fill up the deficit. That's what these energies do exactly. Okay, so if you watch this process every day, suddenly you feel that maybe this is what this ancient philosopher so this one originally has sound, but the sound doesn't make any difference. So you just watch these. You know, this is basically a month full, but I'm just going to play it for a little while to see it. Doesn't seem to go. Oops, sorry. Yeah, it's going. So you can watch this kind of weather loop come and go every day. This is the nighttime, and that's the daytime. You can see clouds all over the earth, and it goes in all kind of ways. And you feel it you also get a sense that all those patterns goes up and comes back. It comes back in time about half a year, 6 months. So it somehow give me that this is actually what this ancient philosopher Zhuangzi actually want to say, because he make this fantasy and metaphoric story that you have this legend bird called the pen, whose size is several thousand miles big, and fly up to 90,000 li, or let's say loosely 90,000 kilometers or something, and you've never seen such a bird before. However, this is more or less the size of the natural climate system, well, at least year in, year out. And every time it's about 6 months. 6 months to the north, maybe it's accomplished by fish, and 6 months back to the south, maybe by this bird, match quite well. And why do you think that I can think about this? Because when you study climate, and you do realize that first of all, that's what happens every year. And secondly, Zhuangzi also talk about that there are these ancient trees that use 8,000 years as a spring and 8,000 years as winter. And can that really happen? And yes, it's not really trees. These are called climate cycles. You have these climate cycles. Each cycle can be 8,000 years. And in fact, there are even more, maybe tens of thousands of years. All those cycles. And these are known as the Milankovitch cycle these days. So the ancient philosopher could not explain to other people in terms of science fact, because back then there wasn't too much science fact, but they can feel naturally that there is such a natural rhythm that's working. But clouds are not all the same. There are low clouds, such as the one to the left here. These clouds play the role of cooling because they mostly reflect sunlight without trapping too much heat. On the other hand, high clouds causes warming. Cirrus cloud that I just showed in the early movie, that one really causes global warming. So it depends on a dedicated balance between among the low clouds and high clouds that decides what will be the fate of our climate. Do we know that for sure? No. In fact, to these days, that's the biggest uncertainty that we know of. The IPCC, the Intergovernmental Climate Change Studying Group, actually decided that the cloud factor is the largest uncertainty. So given that the climate is the biggest uncertainty of these days of society, the cloud formation is the biggest uncertainty in the whole climate business. So it seems to fit that you are studying these uncertainties in this digital world. Indeed, climate is one of the most important. Okay, but this is towards near the end. So I hope I have convinced you that clouds are not innocent. They are working hard and they are doing their share of changing the whole world. Okay? And so by that, I end my story. And so I guess since I have given the talk, I'm innocent. Thank you.
We probably have, a few more minutes. So the floor is open for questions and discussion.
So we have climate model, like a very large model, like field dynamics model of the atmosphere. We talked about the slides a little bit. How close are they and how accurate are they basically, this large model?
Very, very large uncertainty. That is why if you read the IPCC AR, they are called the assessment reports. The latest, I think, is AR6, the 6th assessment report, and they admit that it is still with a very large uncertainty. We are more sure these days that there is warming, but how much warming that is really a big uncertainty, because it depends how much cloud you form and where the cloud form. Like I said, the low clouds and high clouds, they're all different. Do we have a precise knowledge of where clouds are and how much are they? No. That's why NASA has been developing these all kind of satellites, try to do such a measurement. But as yet, I know they are not reaching the stage to say that we know now. No, still long time away. Please, Brian. Okay. Well, there are, depends on what effect you're talking about. But one thing, say, if we can do a little weather forecast by watching clouds. Okay, so if you see cloud overnight, you can be sure that tomorrow morning won't be very cold. And why is that? Well, it's because cloud is a good absorber of heat. So overnight, if you have a lot of clouds, when you try to radiate heat away, that night cloud is going to absorb heat and send at least a large chunk of them back. And so the so-called, what in meteorology called the difference between the maximum and minimum temperature will be very small if you have a cloudy night. If you have a night like what we have here, you can expect there's a lot of changes called the diurnal change, because the difference is very large. You don't have clouds. So in the nighttime, this radiation will go away very quickly. Now in the daytime, if you have cloud, what will happen, of course, is that the sun cannot penetrate that easily. So they have to go through this cloud and causes a lot of shadows. And that also limits the amount of heat you can heat the surface. Okay, cloud is a very tricky thing. A lot of people will think that initially, when people study this global warming, say, if you add more carbon dioxide into the atmosphere, what will happen? And people say, of course, it's going to cause warming because, carbon dioxide is a greenhouse gas and so on and so on. But it's not so easy because you have clouds. Suppose you have a lot of carbon dioxide here and causes a lot of warming. What will happen next? What will happen next is that because this place is warmer, it's going to cause convection. When the convection occurs, the air goes up. When air goes up, clouds form. When clouds form, it shields the light to go through. So this place may become colder instead of warmer. And so we need to know this whole thing as a global basis in order to really decide what can happen. And that's a very complicated business. And I believe even to these days, we still don't fully understand all the things. Please.
You give the very interesting and exciting topics about cloud formation. But I would like to ask, what is reason, what the basics, fundamental basis for the cloud formation first? That because of, from point of my view is, the cloud is established or lost, that's because of the diversity, biodiversity lost. Biodiversity means all living organisms, include most likely the plants. When deforestation is heavy deforestation, the more deforestation, the cloud disappear. Look at the desert area, or here in South America of the Mojave Desert. Of course, you mentioned about, you're right, if the less cloud, it will be very hot. And the more cloud will be cooler.
Cooler, right.
And that cooler because of the tree, because of plantation. Keep the warm, keep the heat, absorb the heat because of photosynthesis and respiration. So deforestation is a major cause for the cloud disappear. And I think this is another topics I would like to emphasize is on the climate change due to the loss of biodiversity.
Yeah,
Thank
that's
you.
a point well taken. That's a very important topic also. Thank you. There.
Oh, thank you. Thank you very much. So I really enjoy your talk. I think it's the perfect marriage of the humanities and the science. Right? You make a lot of allusions to poems, to Buddhism as well. And we are a center for Buddhist studies. I feel really, close to your talk. And it looks like the Buddhist monks, they are the earliest kind of researchers of cloud, right?
Yes,
At least they
yes.
observe clouds. But for me, I'm not a scientist, but we study temples, religious sites, for example. So we have this problem dealing with local, region, global, for example.
Mm-hmm.
So for all the kind of empirical studies like cloud, we study only clouds in one small area.
One place,
So
right.
how do you deal with this relationship between this Tuson, for example, Sonora Desert, this cloud system, and the other more larger system in the southwest? And do you actually divide the sky into different regions, for example? So you look at only this area and intensively study this area, and how this small area connected to the global kind of a cloud pattern change, for example?
The quick answer is yes, indeed, the people do such a study. In fact, this is a very important study these days, and to see what will be the response of each area to this change of the climate, because we know that the climate is changing. However, the response of each area is different. For example, I just talked about the outgoing long-wave radiation. And that is already very different in various places. In fact, as far as I know, Tucson is increasing its radiation. First of all, it becomes hotter. And secondly, you radiate more strongly. Over the last 30 years, I think there's a map been plotted. And so in a larger scale sense, that represents what happens. What happens that it actually means your cloud actually is decreasing, the cloud total amount. So there is a global pattern which is more or less explainable. There is local pattern, which is much more complicated. Some places are actually not suffering from global warming, but more like a cooling in a certain period. And so that's fluctuating. What we do know, for example, is that the humidity, the absolute amount of water in the air is increasing. Why? Because you have global warming. And when you're warming, you evaporate water more. So the whole world is full of more water vapor. So if you see newspapers saying that, oh, we got this record rainfall in this place that causes a flood or something, don't be surprised, because the atmosphere has already had more water vapor to begin with. It had to shed such amount of rain in order to get balance. On the other hand, talking about relative humidity, which is, a amount to say that how saturated the air is. The global humidity, relative humidity is decreasing. So instead of becomes more humid, it actually becomes less humid. So which are the absolute humidity is increasing, but the relative humidity is decreasing. So these two already says there's a change in terms of the cloud in different regions. And there is a study, well, there's quite a few studies, but the main theme is that in this global change pattern, the rich becomes richer and the poor becomes poorer. Those original without cloud will become even less. Maybe that's why the case in Tucson here. Those places with a lot of clouds in general gets more clouds, and those places with a small flood before now becomes a huge flood. So the distribution becomes less even under this current change. So that is really related to your question. Different parts of the world has different cloud pattern, and they're going to suffer different kind of climate change.
Well, we're running out of time, and well, I got a brand new understanding to, for example, like Town Point, Wang Wei, who is also a lay Buddhist. 行到水穷处，坐看云起时。To the water's ending, see the cloud rising. So it's truly an inspiring, lecture which direct us or redirect us to the fluid, dynamics and mechanism of the cloud formation and dissipation in close relation to the global, climate change. So it's a wonderful talk, and we want to thank Professor Wang and thank everyone. Yeah. Okay. Thank you.